I want you to picture um, a deeply unsettling scenario. Just imagine you're standing outside in this big open field on a really gray, blustery day.
Okay, setting the scene.
Right. And the temperature suddenly drops, the clouds break open, and just boom, a massive torrential rainstorm begins.
Oh, wow.
Yeah. Now imagine someone runs up, hands you a clipboard, and gives you your only task for the entire day. You have to pick out a single raindrop, like high up in the sky, maybe a mile up.
Just one drop.
Just one specific drop of water.
Yeah.
And you have to predict exactly, and I mean down to the microscopic millimeter, where that specific drop is going to hit the pavement.
I mean, that's a phenomenal mental image, really, because it perfectly highlights the absolute limits of human perception.
It's impossible, right?
It's a fundamentally impossible task because you've got atmospheric wind shear, you've got microscopic temperature fluctuations, air resistance.
Not to mention it colliding with other drops.
Exactly. The sheer volume of interacting variables acting on that one tiny drop of water makes its exact trajectory completely unknowable. You just cannot model the drop.
You would literally lose your mind trying to track it. You'd just be staring at total chaos. But, this is the paradox. If you zoom out, think about the meteorologist at the National Weather Service.
Right. They don't care about the single drop.
Exactly. They don't track individual raindrops. They look at the radar, they analyze the massive pressure system, and they tell you with, honestly, remarkable statistical confidence exactly how many inches of rain will accumulate in your city over the next 6 hours.
Yeah, because they understand the mechanics of the storm system as an aggregate whole, even if those individual components are pure chaos.
Which brings us to our topic. Welcome to the Deep Dive. Today, we are opening up a set of highly influential notes from a Certificate in Quantitative Finance lecture.
The source text is titled The Random Behavior of Assets, right?
That's the one. And our mission for you today is to decode the actual mathematical machinery that quantitative analysts, the quants on Wall Street, use to make sense of that financial storm.
The ambition here is just thrilling because we're going to build a continuous time asset price model, and we're going to do it completely from the ground up.
No jargon, right.
Right. We're stripping away the jargon, relying entirely on logical deduction, and just basic daily price data.
I love it.
By the end of this discussion, concepts that usually live exclusively behind the carded walls of applied math PhD programs, concepts like stochastic calculus, the Wiener process, the log normal random walk.
Sounds so intimidating.
They do, but they are going to feel entirely intuitive to you by the time we're done.
Yeah, so if the phrase stochastic differential equation makes you want to hit pause, just stick with us. We aren't going to read you a textbook filled with Greek algebra.
No, absolutely not.
We're going to explore the underlying logic. This is essentially a philosophical journey,
Right.
about how humans construct mathematical nets to capture pure randomness.
It really is. And to figure out how we do that, we first have to understand why the quant approach had to be invented in the first place.
Right. The source notes begin by contrasting the quant mindset with how most people traditionally analyze a market.
The text elegantly divides the financial analysis universe into 3 distinct paradigms. And understanding the first two really helps illuminate why the third, the quantitative approach, is such a radical departure.
Okay, so let's break them down. The first paradigm is fundamental analysis.
Right. This is the Warren Buffett school of thought.
Yeah. The fundamental analyst believes a company is a real-world machine that generates cash. So you tear into the balance sheet. Right?
Exactly. You analyze the supply chain, you look at the CEO's track record, and you try to determine the company's quote-unquote intrinsic value.
Right, and the core assumption there is that if the market price is lower than the intrinsic value, you buy it. Because eventually, reality will force the price up to where it belongs.
Precisely. It assumes a rational tether to the physical world. Then you have the second paradigm, which is technical analysis.
The chart readers.
Yeah. The technical analyst believes that human psychology drives the market, and that psychology leaves footprints in historical price charts.
So they're looking for geometric shapes, head and shoulders patterns, moving average crossovers, support and resistance lines.
Exactly. They believe history repeats itself because human greed and fear repeat themselves.
But the author of our source text tosses both the fundamental balance sheets and the technical geometry completely out the window, like totally discards them.
Yep. We are focusing exclusively on the third paradigm, quantitative analysis.
And the justification for throwing out those first two paradigms becomes really obvious when you look at the raw data the author presents, because the text includes a price chart of the S&P 500 stretching across a massive timeline.
Right, from April 1949 all the way to October 2006.
Over half a century. And when you look at an index chart spanning over 50 years, it is not a clean story of rational growth.
No.
And it's not predictable geometric patterns either. It is a relentless, jagged series of chaotic shocks.
The defining characteristic of that historical line isn't value, and it isn't repeating geometry. The defining characteristic is radical unpredictability.
It seriously looks like the readout of a seismograph during a 50-year earthquake.
That's a great way to put it. And because there is so much noise in that historical line, the author argues that any successful mathematical model cannot be built on the illusion of absolute certainty.
Right, you can't just draw a straight line.
Exactly. The model must be probabilistic. If we are trying to predict the market, we have to speak the language of chance.
And stepping into that probabilistic mindset requires a severe mental abstraction. The text stresses a point that is just foundational. Whether you are modeling the S&P 500 index or a volatile tech stock or a sovereign currency or agricultural commodities, the modeling framework is identical.
The math does not care what the physical asset actually is.
I really have to pause here because this is where my human brain naturally rebels.
Oh, sure.
Because if I'm buying a physical barrel of West Texas Intermediate crude oil, that is a highly tangible object. It sits in a massive steel tank.
Right.
It has real storage costs.
It can literally catch fire.
Yes, it can catch fire. It's dictated by OPEC policies and global shipping lanes. On the other hand, if I buy a share of a cloud computing software company, that is a purely theoretical claim on future digital revenue.
Very different things.
Right. One powers tractors, the other runs servers. How can a mathematical model treat them as identical entities without losing touch with reality?
It is the ultimate reductionist approach. Quantitative analysis deliberately severs the tie to physical reality because physical reality is just too messy to model at scale.
So it just ignores the mess.
It treats the asset simply as a theoretical vehicle that generates a time series of relative growth. All of the tangible specifics, the oil refinery fires, the software bug in the cloud company, the geopolitical crisis.
All those physical causes.
Yes, all of those distinct physical causes are homogenized into a single unified effect, a change in price.
So the fundamental cause of the price movement is totally irrelevant to the quant. The only thing that matters is the footprint it leaves behind.
Right.
And that leads to the most important rule in the source notes. You must ignore the absolute dollar value of the asset.
This is crucial.
Like a stock trading at $1,000 a share is not inherently stronger or better than a stock trading at $10 a share. The dollar price is just a coordinate. The only metric that actually matters is the return.
Return is the great equalizer in finance. It strips away the denomination and measures pure relative performance.
Okay, so let's define return.
The formula is intuitive. You take the change in the value of the asset over a period of time, add any cash flows it generated like a stock dividend or a bond coupon, and divide that total by the original value of the asset.
I'm going to try to visualize this. Imagine two runners in a marathon. Absolute price is their exact GPS coordinate on the race course.
Okay.
But return is their pace, their rate of acceleration. If you only look at the GPS coordinates, you just know runner A is at mile 10 and runner B is at mile 5.
Which just tells you who started earlier or who has been running longer.
Exactly. But if you want to model their future performance, you need to know their relative speed. A runner accelerating by 5% every mile is a fundamentally different investment than a runner decelerating by 2% a mile, regardless of where they currently are on the track.
That captures it perfectly. By converting raw prices into percentage returns, we create a standardized apples-to-apples environment.
Makes sense.
If a $1 million commercial property goes up $10,000, that is a 1% return. If a $100 bill in a savings account earns $1 in interest, that is also a 1% return.
Wow.
In the eyes of the mathematical model, those two assets just performed identically.
We've abstracted away the skyscraper and the dollar bill and turned them both into pure vehicles for yield.
Exactly.
Okay, so once we've shifted our perspective to only look at these percentage returns, how do we actually begin constructing the model? I mean, how do we measure the storm?
We have to break the data down into discrete, manageable steps. The source material begins at the daily level.
Day by day.
Right. It introduces a notation convention to track this. The return from today, which we will call day I, to tomorrow day I plus 1, is denoted simply as R sub I.
So R sub I represents the percentage jump or drop over one single day.
Correct.
And the author runs this calculation on decades of daily S&P 500 data. They take the closing price tomorrow, subtract the closing price today, and divide by the closing price today. And when you look at the raw numbers that pop out of that massive spreadsheet, they are almost comical because of how microscopically small they are.
They are entirely unintuitive to the average investor because over the sampled half-century period, the author calculates the daily mean return. This is the underlying drift of the market, the average daily forward progress.
Okay, what's the number?
That number is 0.000035.
Wait, 0.000035?
Yes.
That is 3.5 basis points, 0.035%. If I had $10,000 invested in the S&P 500, my expected statistical gain on a random Tuesday is, what, roughly $3.50?
Yeah, about $3.
It is a whisper of growth.
It is, but the mean is only half the story. The other half is the violence of the movement around that tiny average. The author calculates the sample standard deviation for the daily returns, which measures the typical daily swing up or down.
The turbulence.
Right, and that number is 0.08909, or about 0.89%.
Okay, that dynamic is staggering when you lay it out like that. The average forward step is 3.5 basis points, but the typical random shove forward or backward is almost 90 basis points.
Exactly.
So the chaotic noise is roughly 25 times larger than the actual forward progress on any given day. You are taking one tiny step forward, while a tornado throws you 25 steps in random directions.
That's exactly what it feels like. And to extract a coherent shape from that tornado, the quant process requires standardizing the raw data. This is a crucial statistical maneuver.
How does that work?
They take every single daily return over that 50-year period, subtract that tiny average return of 0.000035, and then divide the result by the standard deviation of 0.0008909.
But why perform that specific translation? Like, what does subtracting the mean and dividing by the standard deviation physically do to the historical data?
It centers the data and standardizes the scale. By subtracting in the mean, you shift the entire data set so its new average sits at exactly 0.
Ah, okay. So you are stripping away the specific 50-year upward drift of the U.S. economy.
Exactly. Then, by dividing by the standard deviation, you scale the width of the data so the standard deviation becomes exactly 1. You are essentially taking the unique, messy fingerprint of the S&P 500 and forcing it into a universal statistical mold.
Wow. And when the author plots this standardized data on a histogram, the result is breathtaking.
It really is.
Because the chaotic, jagged history of the stock market somehow organizes itself into a shape. And it's the most ubiquitous shape in all probability. Gaussian distribution, the bell curve.
The emergence of the normal distribution out of raw market chaos is the bedrock of classical quantitative finance.
That's kind of beautiful.
The text introduces the probability density function for this curve. Without getting bogged down in the massive formula, it basically describes a perfectly symmetrical shape defined by the exponential mathematical constant E.
We don't even need to read the formula to visualize the reality. Just think about that perfect bell shape. The massive peak in the center represents all the perfectly mundane trading days.
Right.
Days where the market nudged up or down a tiny fraction of a percent. The vast majority of daily returns cluster tightly around 0. Then, the curve slopes downward symmetrically on both sides.
As you move further out to the edges, the tails of the bell, you find the dramatic 2% or 3% days.
And way out in the extreme, microscopic slivers of the tails, you find the massive boom days and the catastrophic crash days. The curve tells us that those extreme events are mathematically incredibly rare.
And this specific shape gives us our very first working model. It is a discrete time model operating day by day.
So we actually have a formula now.
Yes. We can finally write a mathematical equation for tomorrow's return. The daily return, R sub I, equals the mean, plus the standard deviation multiplied by a variable the text designates as the Greek letter phi.
Okay, let's unpack this. Tomorrow's return equals the mean, plus the standard deviation multiplied by phi. And phi is the engine of chaos in this equation, right?
Exactly.
It represents a single random draw from that perfectly symmetrical bell curve we just built.
Let's contextualize what that equation physically represents.
Think of the market as a massive machine that powers on every morning at 9:30 a.m. First, the machine idles forward at a fixed, reliable speed. That's our mean of 0.000035. The gears are turning.
Slowly.
Very slowly. But before the closing bell rings, a giant lever is pulled. The machine reaches into a huge hat containing millions of slips of paper.
Okay, I like this.
Most of those slips have numbers very close to 0. A few have larger numbers, like 1 or -1. A tiny fraction have extreme numbers, like 3 or -3. The machine draws a single slip that is our phi value. It multiplies that number by our standard deviation, and that dictates how hard the machine gets violently shoved off its path before the day ends.
That is a highly accurate mechanical translation of the formula. The mean is the underlying deterministic drift, and the phi term provides the stochastic or random turbulence.
It's a great model.
But we have to address a profound underlying question here. Why does the Gaussian distribution appear in the first place?
Oh, that's a good point.
Why does human behavior, millions of independent traders buying and selling based on fear, algorithmic signals, random news events, naturally assemble into a perfectly symmetrical mathematical curve?
It's an incredible phenomenon
Yeah.
because nobody is orchestrating it. The retail trader buying fractional shares on their phone isn't coordinating with the algorithmic trading server in New Jersey to ensure their combined trades form a bell curve. It just happens organically.
It emerges because of a principle known as the central limit theorem. While the author doesn't explicitly name the theorem in these notes, the entire framework depends on it.
How does it work?
The theorem basically states that when you aggregate a massive number of independent, identically distributed random variables, their normalized sum tends toward a normal distribution, completely regardless of the underlying distribution of the individual variables.
Meaning, it doesn't matter how weird or chaotic the individual raindrops are. If you have enough of them, the aggregate system acts like a smooth fluid.
Exactly.
The collective noise of millions of individual decisions cancels itself out into this pristine statistical bell.
Yeah.
But, I want to plant a massive flag here, because the source material does something highly unusual for a quantitative textbook.
It admits a flaw.
Yes, it immediately admits a flaw. The author explicitly notes that assuming a normal distribution is, quote, not perfect, but is a good starting point. They promise that before the lecture is over, we have to explore where this simple model goes wrong.
It is a critical admission. We are building an elaborate, highly functioning mathematical cathedral, but the architect is pointing out that the bedrock has a slight fracture.
We will definitely return to that fracture at the end of our journey. But for now, we have a functional daily model. However, it is a discrete model. It ticks forward exactly once every 24 hours.
And the author argues that this is fundamentally insufficient, that our next vital goal is moving the model from discrete time into continuous time.
The reasoning the text gives is deceptively simple. It says, maths is easier in continuous time, which sounds entirely backward to anyone who has ever tried to do mental math.
Oh, I know.
It feels like dealing with nice, clean, daily chunks should be infinitely easier than dealing with a continuous, flowing stream of milliseconds. Why does continuous time make the math easier?
Because discrete steps are jagged. If you try to draw a curve using daily steps, you get a staircase. And classical calculus, the mathematical toolkit we use to analyze rates of change, find slopes, optimize functions, was designed by Isaac Newton and Gottfried Leibniz specifically to handle smooth, continuous curves.
Oh, so calculus hates staircases.
Yeah. Calculus struggles profoundly with staircases. If we want to unlock the full analytical power of mathematics to predict market behavior, we have to smooth out the staircase. We have to figure out how our parameters, the mean, and the volatility behave when we shrink our daily time step down to practically zero.
Okay, we need to figure out the scaling laws of the market. Let's tackle the predictable part first. The mean, or the underlying drift. The text poses a foundational question. If the average expected return over a single day is 1%, what is the expected return over a full week?
Assuming a standard 5-day trading week, the intuitive answer is correct here. It is 5%.
Really? Just 5 times 1?
Yep. The predictable drift of an asset scales linearly with time. If you double the duration of the investment, you double the expected underlying growth.
So mathematically, the mean equals mu multiplied by delta t. Mu is our annualized growth rate, and delta t is the size of our time step.
Correct. Let's anchor this with the S&P 500 data from the notes. We know the historical daily mean was 0.000035. So 0.00035 equals our annualized drift, mu, multiplied by our time step. But how do we define a daily time step in relation to a full year?
The text uses a very specific fraction, 1 divided by 252. Now stop the tape.
Yeah.
There are 365 days in a year. By using 252, we are mathematically deleting over 100 days from reality. Are quants suggesting the universe ceases to exist on Saturdays, Sundays, and federal holidays?
It does sound absurd, but it highlights the difference between calendar time and market time. A mathematical model only cares about exposure to variance.
Okay.
Think about it. On a Saturday, the equity market is closed. The asset is not actively trading. There's no price discovery, no bid-ask spread fluctuating, no massive volume of buyers and sellers clashing to update the price.
It's frozen.
Exactly. For the purpose of generating returns and volatility, Saturday is an empty void. So the time step, delta T, is calculated strictly based on the approximate 252 business days in a trading year.
Time, in this context, is the duration of active exposure to the storm.
Well said.
If you solve the algebra using that 252-day convention, Dayton 0.000355 equals more times 1 over 252, you find that mu, the annualized growth rate, is 0.0882, or 8.82%.
Which is a historically accurate reflection of the broad U.S. equity market's long-term performance. Now let's observe how this linear drift behaves as we push it toward continuous time.
Okay.
To isolate the mechanics, let's temporarily pretend the market has no randomness, no volatility at all. If we only have the drift, tomorrow's price is simply today's price multiplied by our growth factor. S sub I plus 1 equals S sub I times 1 plus mu delta T.
It is literally the basic formula for compound interest. If I start with $1,000, which is S0, after one day I have S0 times 1 plus mu delta T.
Right.
On the second day, I take that entire new amount and multiply it by 1 plus mu delta T again. So it becomes S0 times 1 plus mu delta T squared.
And if you compound that over an arbitrary number of steps, which we will call M, the general formula becomes the starting price S0 multiplied by 1 plus mu delta T to the power of M.
Got it.
To force this discrete compounding formula into continuous time, the author performs a brilliant classic mathematical translation using logarithms and exponentials.
The notes move incredibly fast here. They rewrite the formula S, 0 times 1 plus mu delta T, to the power of M, as S0 multiplied by the mathematical constant E, raised to the power of M times the natural logarithm of 1 plus mu delta T.
It's a mouthful.
It really is. And if I'm compounding daily steps, why does Euler's number E suddenly appear out of nowhere?
The constant E, which is approximately 2.718, is the fundamental speed limit of continuous growth. It was discovered precisely by mathematicians trying to figure out compound interest.
How so?
If you compound a rate annually, you get a certain amount. If you compound it monthly, you get slightly more. Daily, even more. But it doesn't grow to infinity. As the compounding intervals get infinitely small, as you compound every millisecond, every microsecond, the return hits a hard mathematical ceiling governed by the constant E.
Oh, wow.
So whenever you transition from discrete steps to continuous flowing growth, E naturally surfaces as the foundation.
So we use E and natural logarithms to bridge the gap. When our time step delta T becomes infinitesimally small, the natural logarithm of 1 plus mu delta T essentially flattens out and becomes virtually identical to just mo delta T.
That approximation is the key. The massive exponent simplifies beautifully. The whole equation reduces to S0 multiplied by E raised to the power of mo times M times delta T.
Now think about what M times delta T actually is. If M is the total number of steps I took and delta T is the size of each step, multiplying them together just gives me the total time I've been walking. M times delta T is simply total time T.
Exactly. So as our individual time step shrinks down to literal zero as the discrete staircase vanishes, we're left with a perfectly smooth deterministic curve. S of t equals S0 times e to the power of ma t.
It is the formula for a continuously compounding savings account, money smoothly sweeping upward in an exponential curve.
Yeah.
The author makes a compelling point here, too. If the mean scaled with any other power of time besides being strictly linear, the entire model would break.
Completely shit.
If the exponent was slightly higher, the asset price would instantly explode to infinity. If it were slightly lower, the asset price would flatline. Linear scaling is the only physical reality that allows stable, continuous growth.
So we have successfully transported the predictable half of our market model into continuous time, but the predictable half is the easy part.
Right. Now for the hard part.
Now we have to grapple with the unpredictable half, the volatility. And this is where human intuition utterly fails and where the core genius of stochastic calculus begins.
This is the cognitive hurdle that trips up almost everyone. We just proved that drift scales linearly.
Right.
1% a day means 5% a week. So we asked the exact same question regarding the random noise. If the standard deviation of our returns is 1% over a single day, what is the standard deviation over a 5-day week?
The author provides a blunt warning. The answer is absolutely not 5%. You cannot simply add standard deviations together.
But if the underlying growth adds up linearly day after day, why doesn't the volatility add up linearly?
Because of the defining nature of the noise, The daily returns are independent random variables.
Let's clearly define what independent means in this context, because it is the linchpin of the math.
Independence means the market has no memory.
None at all.
None. If the S&P 500 experiences a massive, volatile 3% spike on Monday, that event imparts zero physical force on Tuesday's movement. Tuesday's coin flip is completely fresh. The volatility of Tuesday does not care about the volatility of Monday.
Because they are completely independent, the chaotic shocks inevitably work against each other over time. You might have a violent 2% upswing on Monday, but a 1.5% downswing on Tuesday.
Exactly.
You experienced extreme daily volatility, but your net position barely moved. The positive and negative shocks partially cancel each other out. To use an analogy, imagine you are blindfolded in a massive open parking lot.
Okay, blindfolded in a parking lot.
You are taking a random walk. Every second, you take a single 1-meter step. But the direction is completely random, forward, backward, left, right. You do this for 100 seconds. You have exerted 100 meters worth of walking energy. Are you 100 meters away from where you started?
Mathematically, the odds of you ending up exactly 100 meters away are vanishingly small. That would require you to randomly choose the exact same direction 100 times in a row.
Right. Because my steps are random and independent, I'm constantly doubling back. I take a step north, and then my next random step might be south, entirely canceling out my progress.
Yes.
After taking 100 random 1-meter steps, the laws of probability dictate that I will likely only be about 10 meters away from my starting point. What is the relationship between 100 steps and 10 meters of displacement? 10 is the square root of 100.
That is the perfect spatial translation of the math, but we need to prove it algebraically. The source notes explain that while you cannot add standard deviations, you can add variances.
Why variances? What makes variance the additive property here?
Think about the geometry of probability. Because the daily shocks are completely independent, you can visualize them as acting at right angles to one another. They are orthogonal.
Okay, like a grid.
Exactly. If you move 3 units east and then 4 units north, your total displacement isn't 3 plus 4. You don't add the distances directly. You use the Pythagorean theorem. A squared plus b squared equals c squared.
Oh, right. 3 squared plus 4 squared is 5 squared. So 25. And the square root is 5.
Exactly. Your total displacement is the hypotenuse, which is 5. In statistics, standard deviation is the length of the side of the triangle. Variance is the square of the side. Just as you can only add the squares of the sides in geometry, you can only add the variances of independent events in probability.
That clicks everything into place. Variances are the squared building blocks we are allowed to stack. The author then walks through a proof to find the scaling law. They propose a hypothetical. Let's assume standard deviation scales at the time step, delta t, raised to some unknown exponent. Let's call that exponent alpha. Standard deviation equals delta t to the alpha.
If standard deviation is delta t to the alpha, and variance is standard deviation squared, then variance must scale as delta t raised to the power of 2 alpha.
Okay, so the variance of a single time step is delta t to the 2 alpha. Now we need to figure out the total variance over a long period of time, t. How many individual steps are in that period? It's a total time t divided by the size of the step delta t. So t over delta t is the number of steps.
We take the total number of steps and multiply it by the variance of each individual step. So 2 divided by delta t multiplied by delta t to the 2 alpha.
Using basic exponent rules, dividing by delta t is the same as subtracting 1 from the exponent. So the total accumulated variance over time, t, simplifies to t multiplied by delta t to the power of 2 alpha minus 1.
This is where we run the continuous time experiment. We need to shrink delta t down to 0. We're asking the math, what happens to the total variance as our time steps become infinitesimally small?
Right.
We know from reality that a stock market has a stable, measurable amount of volatility over a year. The total variance cannot be 0, and it cannot be infinity.
Because if the exponent 2 alpha minus 1 is a positive number, then as delta t shrinks to 0, that entire variance term crushes down to 0. The noise vanishes. The market becomes a perfectly predictable, deterministic machine. We know that is demonstrably false.
Conversely, if the exponent 2 alpha minus 1 is a negative number, then as delta t shrinks to 0, you are essentially dividing by 0. The variance term explodes to infinity. The asset price would instantly jump to infinity or 0. Total chaos. Also demonstrably false.
Therefore, there is only one mathematical reality that allows the variance to remain a stable, finite number as time becomes continuous. The exponent must equal exactly 0. So 2 alpha minus 1 equals 0. If you solve for alpha, you get alpha equals 1/2.
And raising a value to the power of 1/2 is identical to taking its square root. We have mathematically deduced the foundational law of quantitative finance. Standard deviation scales with the square root of the time step. Standard deviation equals a constant parameter multiplied by the square root of delta t.
That constant parameter is denoted as sigma, which the author defines as the annualized volatility. Let's quickly check the math using the real S&P 500 data. We know the daily standard deviation was 0.008909. Our time step delta t is 1 day, or 1 over 252 of a year. So 0.008909 equals sigma multiplied by the square root of 1 over 252.
If you do the calculation, sigma equals 1141, or 14.1%. This is our finalized measure of the asset's intrinsic turbulence scaled to a full year.
This is a monumental breakthrough at our model building. We have isolated the two distinct engines driving the asset's price, and we know exactly how time fuels them. Growth scales linearly with time. Volatility scales with the square root of time. Let's bolt the pieces together and look at our completed discrete time equation.
The full equation is structured logically. S sub I plus 1 minus S sub I represents the change in the asset's price from today to tomorrow. That change is equal to two parts added together. Part 1 is the predictable drift, 1 times S sub I times delta t. Part 2 is the random shock, sigma times S sub I times phi times delta t to the 1/2.
Tomorrow's price change equals a tiny sliver of guaranteed growth, plus a massive random shock driven by the roll of our Gaussian die, phi, and the square root of time. The notes emphasize that this specific equation is the beating heart of Monte Carlo simulations.
Monte Carlo simulations revolutionize risk management and derivative pricing because you cannot predict the exact sequence of phi values, the specific random shocks. You let a computer simulate reality.
Oh, I see.
You program this discrete equation into a server and have it calculate tomorrow's price. When it hits the phi term, the computer randomly draws a number from a bell curve. Then it does it for the next day and the next, projecting the asset's path a year into the future.
It just runs that.
It repeats this process 1,000,000 times, generating 1,000,000 possible alternate realities for the S&P 500. By analyzing the final distribution of those 1,000,000 paths, quants can accurately price complex options and map out the exact probability of a catastrophic portfolio loss.
That is amazing. But staring at the architecture of this equation reveals a fascinating, violent tug-of-war between the two terms. And the victor of that war depends entirely on the horizon of your observation. It all comes down to the bizarre math of fractions and square roots.
Let's explore the mathematics of small intervals. Let's assume you are trading at high frequencies, so your time step, delta t, is incredibly small. Let's say delta t is 0.00001. The predictable drift component of the equation is multiplied by 0.0001. It is vanishingly small, but the volatility component is multiplied by the square root of 0.0001.
Wait, the square root of 0.00001 is 0.001?
Exactly. Compare those multipliers. Taking the square root actually makes the number exponentially larger relative to the linear time step.
This mathematical quirk dictates the physical reality of the market. Over very short intervals, minutes, hours, or days, the delta t to the 1/2 volatility term is mathematically hundreds of times larger than the linear delta drift term.
Wow. The random noise utterly dominates the signal. The forward growth is practically invisible underneath the violent thrashing of the random shocks.
Here's where it gets really interesting. Think of our earlier analogy of walking the blindfolded path. But imagine you are also walking a massive, hyperactive dog on a very long leash.
Oh, this is a great visual.
Second by second, you are getting violently yanked left, right, and backward by the dog. That is the delta day to the 1/2 volatility dominating the short term. If someone watches you for 5 seconds, they would conclude your movement is entirely chaotic.
They think you're crazy.
Right. But if you just keep taking steady, microscopic steps forward, and they film you from a drone for 3 hours, they will see that despite the chaotic yanking of the dog, the entire system, you and the dog, slowly migrated across the park.
Over long time scales, the short-term random variances cancel each other out just enough that the linear drift, the delta term, finally overpowers the noise and becomes the dominant vector.
It is the difference between day trading and retirement investing. The source text provides a brilliant visual representation of this tug-of-war. The author plots the expected path of the S&P 500 on a logarithmic chart.
We should clarify why they use a log chart. As we established, the underlying drift is compounding exponentially. If you plot exponential growth on a standard linear chart, It curves violently upward, which is hard to analyze.
Right, it looks like a hockey stick.
Exactly. Plotting it on a logarithmic scale flattens that exponential curve into a clean, straight, diagonal line.
So on this chart, the pure expected drift is a straight diagonal line ascending to the right. But reality never follows the pure expected drift. So the author plots the boundaries of uncertainty, one standard deviation above and below that central line. And the shape those boundaries create is incredibly revealing. They form expanding parabolas.
This threw me initially, too.
Right, because if the central expected path is a straight line, shouldn't the boundaries of uncertainty just be straight parallel lines hovering above and below it, like a tunnel? Why do the boundaries curve outward into a parabola?
Because of the scaling law we derived. The uncertainty, the standard deviation, does not grow linearly with time. It grows proportional to the square root of time. If you plot a standard square root function on a graph, it creates a parabola lying on its side.
Oh, I see.
As time marches forward, the potential range of where the asset price could be expands, but the rate at which it expands slows down. The parabolas widen, but they widen less aggressively as the years go on.
It is a profound image.
Yeah.
They took the pure, unadulterated chaos of a half-century of market data and boxed it inside a straight line encased by mathematical parabolas. It is a stunning intellectual achievement.
It is.
However, we are still trapped in the discrete world. We are still taking steps, even if they are microscopic steps. The grand finale of this lecture is crossing the threshold to true continuous time.
Taking the limit as delta et approaches zero is where traditional mathematics breaks down and where quantitative finance finds its unique identity. As we transition to continuous time, our notation must shift. The discrete, finite time step delta t shrinks into the infinitesimal differential dt.
Okay, so delta t becomes dt.
Consequently, the discrete change in our asset's price, S sub I plus 1 minus S sub I, becomes the instantaneous rate of change, ds.
So the left side of our equation transitions smoothly. The change in price is ds. The first term on the right side, the predictable drift, also transitions smoothly. Nu s sub I delta t simply becomes mu s dt. The deterministic engine maps perfectly into Newtonian calculus.
Yep, completely fine.
But the volatility term, the sigma s sub I phi delta t to the 1/2, this is where we hit a massive mathematical wall.
We hit a wall because of that square root. You cannot simply drop the infinitesimal dt under the square root and write dt to the 1/2.
Why is that a violation of the rules? If delta t smoothly becomes dt, why doesn't the square root of delta t smoothly become the square root of dt? What breaks?
Newtonian calculus breaks.
Literally breaks.
Literally. The entire machinery of traditional derivatives and integrals relies on a core assumption that curves are ultimately smooth. Think about a circle. If you zoom in close enough on the edge of a circle, the curve flattens out and appears to be a straight line. Because it appears straight at a microscopic level, you can draw a tangent line to it, calculate its slope, and find the derivative.
That is how traditional calculus analyzes change.
But a random walk doesn't behave like a circle.
Exactly. A random walk is fundamentally a fractal. Think about a stock chart. If you look at a yearly chart, it's jagged. If you zoom in on a single month, it doesn't smooth out, it's still jagged. If you zoom in on a single minute of algorithmic trading, it remains infinitely jagged.
It exhibits scale invariance. Because it never smooths out into a straight line, no matter how microscopically you zoom in, it is mathematically non-differentiable. You cannot draw a tangent line to a jagged point. Therefore, traditional calculus cannot process operations on an infinitely jagged path using dt to the 1/2. The derivative is undefined.
The machinery Newton built to track the smooth orbits of planets completely stalls out when trying to track the jittering chaos of a financial market. So how do the quants bridge this gap? If standard calculus fails, what replaces it?
They adopted a new framework called stochastic calculus, and to make the transition, mathematicians realized they had to completely rip out the clunky discrete terms, the random normal draw phi and the troublesome delta t to the 1/2, and replace them with a unified continuous time construct. The text introduces this construct as dx.
dx. The text notes that dx represents an increment of a Wiener process. Now let's address the terminology. A Wiener process sounds bizarre to anywhere outside of a mathematics department. Who is Wiener, and why is this process the key to unlocking continuous chaos?
The name honors Norbert Wiener, a brilliant American mathematician. In the 1920s, Wiener rigorously formalized the mathematical properties of one-dimensional random walks. He was particularly focused on modeling Brownian motion.
Brownian motion. named after Robert Brown, the botanist who looked through a microscope in the 1800s and noticed that tiny grains of pollen suspended in water were constantly jittering around, seemingly under their own power.
Exactly. They were jittering because invisible, microscopic water molecules were constantly bombarding them from random directions. That physical reality, a particle being relentlessly bombarded by random noise, is the exact conceptual model of an asset price being bombarded by random trading
That's a
orders.
perfect parallel.
A French mathematician named Louis Bachelier first proposed this connection in 1900, but Norbert Wiener provided the rigorous mathematical foundation. The Wiener process is the mathematical bridge that allows us to perform calculus on fractal, non-differentiable paths.
So how does this dx term actually function in the equation? The text outlines two defining statistical properties of dx. First, it says dx is a random variable drawn from a normal distribution with an expected mean of 0. So E of dx equals 0. That makes intuitive sense. The continuous stream of random noise shouldn't have a built-in bias pushing it up or down.
Right, it centers the noise. But the second property is the breakthrough. The expected value of dx squared, which, as we discussed earlier, represents its variance, is equal to exactly dte of dx squared equals dt.
Wait, let me trace the logic here. If the variance of dx is dt, then the standard deviation of dx must be the square root of dt.
Yes.
It's the exact same square root of time-scaling law we derived earlier. They didn't abandon the rule, they just elegantly smuggled it inside this unified concept of dx.
You hit the nail on the head. The Wiener process perfectly preserves the essential square root of time scaling, but it packages it in a mathematically rigorous framework that survives the transition into continuous time. It replaces the clunky discrete coin flips with a smooth, continuous flowing river of pure statistical noise. And with that substitution, we arrive at the summit.
The master equation.
The author presents the final foundational stochastic differential equation.
The equation that powers the quantitative financial world. Let's state it clearly. ds equals mu s dt plus sigma s dx.
Let's translate the symbols back into the reality they represent. The instantaneous change in the price of the asset, DDS, is equal to two continuous forces. First, the predictable deterministic engine of exponential growth over time, which is mu s dt.
Right.
Second, the chaotic, unpredictable storm of volatility bombarding the asset at every instant, which is sigma s dx.
It is breathtakingly simple when you break it down into its anatomy. It takes a universe of infinite complexity, the millions of traders, the geopolitical news, the earnings reports, and cleanly cleaves it into two distinct, mathematically manageable forces, the known and the unknown.
It is arguably one of the most successful mathematical equations ever applied to human behavior. This specific equation is known as the log-normal random walk. It is the absolute bedrock of quantitative finance. Decades of Nobel Prize-winning research, including the famous Black-Scholes options pricing model and modern algorithmic risk management frameworks, are built directly on top of the assumptions contained in the single line of mathematics.
Before we wrap up, we need to clarify one last piece of terminology. The equation is called the log-normal random walk. We spent the entire discussion proving that the daily returns form a normal distribution, the standard bell curve.
All right.
Why does the final continuous model use the term log-normal? What is the distinction?
The distinction is the difference between returns and prices. We established that the percentage returns are normally distributed. You can have a positive 5% return or a negative 5% return. The bell curve extends into negative territory.
Okay.
But the absolute price of a stock, the S in our equation, cannot drop below 0. An equity share cannot be worth negative $50. 0 is a hard floor.
Right. There is limited downside, but theoretically infinite upside.
Because of that asymmetry and the mechanics of compounding, if the returns are normally distributed, the resulting absolute price of the asset forms a log-normal distribution. A log-normal curve is bounded by 0 on the left, but possesses a long, sweeping tail extending infinitely to the right. It perfectly models the physical reality of limited liability assets.
So what does this all mean? Let's take a breath and survey the intellectual terrain we just crossed. We began by staring at a wildly chaotic chart of the S&P 500. We realized that to map the storm, we had to abandon our intuition about fundamental value and treat assets simply as abstract vehicles for generating percentage returns.
Right, stripping away the physical asset.
We discovered that hidden deep within the daily noise was a pristine mathematical shape, the normal distribution born out of the central limit theorem.
We then explored the profound ways that time dictates risk. We proved that while predictable growth scales linearly, Random volatility scales with the square root of time, creating a fascinating physical reality where noise masks the signal in the short term, but fundamental drift prevails in the long term.
Finally, we confronted the jagged fractal nature of random walks, discarded Newtonian calculus, and embraced the Wiener process. This allowed us to crystallize the log-normal random walk equation. ds equals mu sdp plus sigma sdx. As the source text concludes, while you might need to introduce slight modifications to model assets with seasonal realities like natural gas prices spiking during winter, this core stochastic framework is the universal translator for global finance.
It is a triumph of applied mathematics. But, as we promised earlier, we cannot leave without examining the crack in the foundation.
Right, the author's warning.
The author explicitly warned us at the beginning that assuming a normal distribution is not perfect and that we must understand where this simple model goes wrong.
We've built the cathedral. Now, where is the structural flaw?
The flaw lies in the tails of the bell curve. Challenge yourself with this conceptual puzzle. If this beautiful equation, ds equals mu sdt plus sigma sdx, relies entirely on the perfection of the Gaussian bell curve to define its randomness, then catastrophic market crashes should be essentially mathematically impossible.
Because the tails of a normal distribution drop off so sharply.
Exactly. According to the strict probabilities of a pure normal distribution, an extreme shock like the 1987 Black Monday crash, where the market dropped over 20% in a single day, is an event that is mathematically so many standard deviations away from the mean that it shouldn't occur, even if the stock market existed for billions of years. It is a statistical phantom.
It's an 8 or 9 sigma event. On a perfect bell curve, the probability is practically zero.
And yet they happen. Black Monday happened. The 2008 financial crisis happened. The 2020 pandemic flash crash happened. These catastrophic shocks occur roughly once a decade. So what does that tell us about our foundational assumption? It tells us that the noise of human panic, the cascading liquidity vacuums caused by automated selling, does not actually fit neatly into the gentle sloping tails of the Gaussian curve.
Tails aren't thin, they are fat.
The tails are incredibly fat, and that is the terrifying reality that lurks outside the bounds of this beautiful model. The log-normal random walk is an incredibly effective tool for managing risk during 99% of trading days, but it fundamentally underestimates the probability of extreme catastrophic events. It fails to account for the moments when the millions of independent traders suddenly stop acting independently and a herd mentality triggers a cascading failure.
That is the multi-trillion-dollar paradox at the heart of quantitative finance. We have built an exquisite mathematical cage to hold the storm, and it works flawlessly. Until the storm decides to break the cage, the math tames the chaos 99% of the time. But that 1% is where fortunes are wiped out and financial history is written. Keep questioning the assumptions beneath the formulas. Keep looking at the extreme edges of the curve. And the next time you are caught in a rainstorm, don't drive yourself mad trying to track the path of a single raindrop. Look at the radar. Understand the system.
It has been a genuine pleasure exploring the mechanics of the chaos with you.
Thank you for joining us on this deep dive. We will see you next time.